Okay, hello everyone to today's seminar on interval methods in control engineering. And it's my very great pleasure to have Radoslav Paulen from the Slovak Technical University in Bratislava today as our speaker. Rado graduated in the field of chemical engineering and process control at the same university in 2008. And after that, he obtained his doctoral degree in the field of process control again at the same university in 2012. Afterwards, he had several positions abroad, for example, at the Technical University in Dortmund, and also is at the Imperial College in London, in the UK. And he was also visiting researcher at the École Nationale Supérieure des Industries Chimiques at the University of Lorraine in Nancy in France. And without further ado, Rado, I'll hand over the microphone now to you to give your talk on convexification techniques for stationary dynamic global optimization and set-based computing.
Thank you, Andreas. Thank you for a very nice introduction. Thank you for the invitation to this seminar. You didn't have to read all those things. I didn't know how long a bio note you want to have, so I put some standard, maybe too long text. But yeah, thank you very much for mentioning all these. You basically see my title slide. What is the first message? You can obtain the slides by scanning the QR code presented here at the lower left, and I also put it's a Google Drive link, and I put it also to our chat. I will also do some other advertisement in the beginning for the project which we are currently working on. It's a collaboration project. It's a networking activity funded by the European Union. This QR code, you can see the website of the project, and we are planning several meetings, conferences, summer schools, whatever you might imagine. This is on basically in automatic control. So if you are interested, you can even subscribe to receive the spams about the events and the newsletter, how the project is going. I said this because to give you time, if you are started to give you time to scan this QR code if you want. What I want to say is I'm happy to give this talk, and I'm happy that that I found during my research life, during my research works, several great colleagues who are attributed here. They and their postdocs, their PhD students, master students contributed basically to what I know about stationary dynamic global optimization, about set-based computing, and we had a great fun dealing with some of the methodologies. And this talk is maybe not showing the very recent progresses. Is more put together as a kind of review talk. I guess, I hope it will inspire some nice discussions where we are standing with the. I'm talking at the interval seminar, so interval methods will be there, where we are standing with these methods, with some other methods, where are the challenges, where are the potential new contributions. So I jump to that, and I will, since this is a kind of review talk, I will not go very deep into many slides, because many of them are relatively rudimentary, but to put us on the same page, I thought it would be a nice thing to be at the base level. This is a standard slide on why do we want to have global optimization. Of course, we want to solve some optimization problem and find its global optimum, minimum, or maximum. Local optima are not what we desire, or we at least want a local optimum with some guarantee that we are not too much far away from the global optimum. And what I will go through, those are basically these four topics. not sure if the time allowed to go very deep over all of them, but you have the slides if you are bored at some part of my talk with some stuff. You can scroll through the slides, and maybe then in the discussion ask me about what are the what I missed, what you would like to hear more about. So I start with the spatial branch and bound algorithm, which I guess many people just know, but it's nice to start somewhere and to illustrate that if we are applying branch and bound algorithm to globally optimize some function, some non-convex function, we basically start by initializing. We have to set where the region of our interest lies, so the most basic constraints that one can deal with. We then solve our original problem. And if we are not lucky, of course, we can get trapped, or we can get a solution that is just the local optimum, and we will call this optimum an upper bound. Why is it an upper bound? Because, well, I never said it, but let's imagine that we are minimizing this function. So local minimum would be not as bad solution, or if we are trying farther, we can only get better. So we only can get lower, hopefully, to the global minimum. We then solve a lower bounding problem, or a relaxed problem, which means that we want to have some method, and this is what the talk is going to be about mostly. We want to have some methodology to construct the convex relaxation or convex underestimator of the blue non-convex function, and this convex underestimator has to fulfill basic two properties. It has to underestimate, so lie below the blue function at each point on our desired interval, and as its name suggests, it should be convex. So if it's convex, we are guaranteed that if we try to now minimize find the minimum of the red function, we found the value of our objective value of our original problem, which might be too idealistic, but it's definitely the lowest possible. Our global optimum of the blue function cannot lie below it. And then we apply the branching. So we are basically splitting our domain of interest, and we continue with finding the upper bound, initializing our local solver somewhere in the region 1 or region 2. And we then we found the two new upper bounds. We can be even forgetting about the upper bound 1. And the next step, we are again doing the lower bounding. So we are finding the solution to the relaxed problem. Now the red functions are constructed separately on the two subdomains on the two subintervals, and one of the properties that we would be desiring when finding a method of constructing the red functions, the convex underestimators, is something which is called convergence. It's usually framed in the term Hausdorff convergence. Basically, when we are shrinking our domain of interest, our convex underestimator, our convex relaxation should get tighter and tighter. So it should get closer and closer to our original function. What we basically can say now, well, we cannot really decide, even though we were already lucky. We found the upper bound, which is actually the solution. Well, but we don't know anything about the blue function extrema around in in the other points. Yeah, only maybe those points which our local optimizer went through its search. So let's just continue branching. Let's pick now this first region for branching. Let's apply lower bounding again. And now we are in a different situation, because now, because of the construction of the convex relaxation of the convex underestimator, we know that the blue function cannot have any value which is below either the lower bound 1 or lower bound 2. But well, this is already contradicting our knowledge that we found the so far best bound on our original problem in a different interval, and we know that in these two intervals we cannot be lower. So we just basically do the fathoming, we discard these two intervals, and then we basically continue branching, lower bounding, and eventually we arrive at the point that where our upper bound and lower bound are not far away from each other. They are just different by the small value epsilon. So we have done a guarantee about the epsilon global optimality of our upper bound of our solution. So, well, I guess this is relatively clear, easy. Yeah, we heard about this, or some of you might be working on this or with this. So then the question is, let's go to the convex relaxation of optimization problems, or what I will call factorable programs. It's no surprise to those of you who are acquainted with the optimization that the convexity or non-convexity of the upper bound or our original problem lies in the objective function. So if we are constructing the lower bounding optimization problem, we need to find the convex relaxation of the objective function, and also the non-convexity can basically lie in the non-convexity of the feasible region. So we also need these. I didn't show it in the trivial example in the previous slides, but also for the constraint functions, we need the convex underestimators. If you are not familiar with that, I give you this slide, which is just a nice illustration. I find it at least nice. If we have if our constraint function is non-convex, let's say it looks like this. The interval x lower bound, x upper bound is our current solution domain. What can we say if we construct the convex relaxation? So again, lower bounding convex function with respect to the blue function g of x. Well, then we can say, okay, if we will include this convex relaxation of G into our optimization problem, well, if we look closer, the red function basically gives us a feasible domain which contains the feasible domain of the previous problem. Yeah, so then we are basically not missing any solution, and our optimization problem in the lower bound is convex. How do we get around this convex relaxation? So this is a formal definition. Now I'm switching to the function f, whether it represents objective or constraints, and well, the two simple properties which I already mentioned: underestimation of the original function f of x, and the convexity. So if we have even a differentiability of the convex underestimator, we can basically pose it already in this or in this form of a Hessian of the function. So one of the interesting convex relaxations, although it looks loose might be this one, another one which maybe goes in a direction of standard interval approaches. Is this here? So well, this is not strictly convex, but still a convex function. It underestimates well, and basically we would have our solution in a very very short time if applying a convex relaxation like this. What I wanna switch even more to is not only looking at convex relaxation, but well, if you just flip our function of interest and we apply again convex relaxation techniques, we would be able to construct the concave overestimator, and that's also coming in handy in several applications if we want to deal with the different sort of a constraints. This basically becomes clear why I'm doing this when we are moving farther and farther. And well, what is one of the approaches how to really construct the convex relaxations for general functions, if we are lucky that they are in a factorable form, which means they are basically analytical functions. It's not like a solution to the differential equation that I will be talking about slightly later. But if we are in the domain of the functions that can be represented in the factor form like this, basically it's building some kind of direct acyclic graph where we say, okay, the first two nodes are the variables x1 and x2, and then one of the node represents this exponential, another node represents this concave function, and so on and so on until our nodes combine to our original function itself. Well, we can then start to look at the sources of the non-convexity. We can direct our method of finding a convex relaxation towards, let's say, atomic non-convexities that might be present, atomic functions that well, we basically know how to deal with. Let me show first of the methods, which is relatively general purpose, and which I guess all of you know very well, the interval arithmetics or the interval analysis, which basically deals with finding under approximation and over approximation of an arbitrary function by applying this set of rules. I'm not going through the rules as this is probably known to you, and what is also probably known to you are these nice little examples where basically you find out if you apply these rules to the innocently looking convex function x squared minus x on some interval 0, 0, 1, well, you basically get not the answer that would look like this. I mean, the tightness of the upper and lower bound of the function, but you get over approximation. Why is this? Of course, this is known as dependency problem. The x is here in too many occasions, so if it looks at first glance strange that you are that you are looking at the different form of a function, but actually this factorization gives you the correct bounds, because the dependency problem x appearing only one time is basically solved here. So this dependency problem, it's interesting, and there are follow-up methods which I'm going to going to show you, which try to somehow address it, but for me it's still an open problem. I would be maybe in the discussion very much looking forward to get to know from you what are your best approaches to dealing with this. Beside the approaches that I will show, even the direct acyclic graph formulation or the factorization, I think it's an open problem to actually formulate your graph, reformulate your graph in a way that the dependency problem is actually minimized or even completely rectified. So another all-purpose method which researchers came up with is alpha BB method, and basically the idea is nice, simple, and neat. That in order to construct the convex relaxation of function f of x, we just subtract a convex inner function from it, and this convex inner function is a quadratic function that basically has its starting points at our interval of interest, x lower bound, x upper bound. So basically then if you just say that alpha, this factor here, is non-negative, then you fulfill the first property of the underestimation. And if you then set alpha as some sort of negatively taken minimum eigenvalue of the interval Hessian of the function f, then basically you fulfill the second property, and your underestimator is convex. So this tries to somehow avoid the problem of dependency by hoping that, well, if we have functions like polynomials, that if we are differentiating, so obtaining the second order information, many of the variables will basically disappear by differentiation. And yeah, this is of course happening. I have a small illustrative example and also counter example at the same time, because here our function, which is here in blue, actually, well, this dependency problem is even exaggerated if we are finding the Hessian of this function, and no wonder then the convex relaxation would look like this. I'm not saying that this method is bad. It has nice convergence properties. It's just if we are looking at the specific details, we want to be maybe cautious what purpose, what type of problems this kind of methods are fit for. Then the great idea, if we are already in the world of factorable functions and we are getting this atomic non-convexities, great idea comes from McCormick, who basically, well, said if I take my two variable non-convexity x times, so bilinearity x times y, well, if I write down this this polynomial, well, what do I have here? My x is definitely greater than the lower bound. My y is definitely greater than its lower bound. So this multiplication has to give me a positive number. But that means that if I expand these terms, then I basically can say x times y must be greater than the rest of these put on the right hand side of this inequality. And we can do this with the upper bound. We can do this with the upper lower bounds, where of course the sign would flip. And now we basically find how to find a relaxation, how to find a upper bounding and upper bound and lower bound envelope of the bilinear terms by having some auxiliary variable w. So basically this is our former non-convexity, and these are the two sandwiches that are, or top and bottom of a sandwich that hold this meat where we are, which we are looking at in our optimization problem. And this can be done not only for trilinear terms, fractional terms. Even there is a composition theorem which basically extends this to any kind of function, and this is how we can work through any factored form of a function. Please don't read these formulas. I'm not going through them. It's just to show it's not at all that difficult to actually have this idea, this nice and neat idea, propagated to a very nice, very wide class of the functions. And in our atomization of the non-convexities, we might arrive at special terms, like there was an exponential in the sixth simple example which I was showing. There might be monomials with the even powers. There might be square roots, logarithms, and all these cases are either convex or concave. So if we are basically trying to bound these, then well, we have we know how to do is the convex case would be, of course, lower bounded, convexly lower bounded by the function itself, and upper bounded by some sort of a second line. Yeah, that's basically the idea. There is even possibility to attack convex or concave cases like this here. That would be some odd powers or odd power monomials, stuff like that. Then what was a nice idea from the researchers was this idea of a Taylor models. That's another way of how to fight with the dependency problem, because the idea is the following. I can represent my function f and how it spread its values over some interval using a polynomial term, which is basically coming from the Taylor theorem, and I can then represent the remainder of the Taylor series using maybe some interval, using interval arithmetics on this calculation. This is the standard calculation of the remainder term of the Taylor series. It's just we are now in the domain where we are not approximating, we are basically bounding. If you are wondering why, if I said that this dashed line is well, it might look like a second order approximation of this red curve, and here it seems that I'm doing this approximation in a midpoint. So why aren't these functions touching? There are just some nice arithmetic rules which are even able to basically shift these polynomial terms such that our interval bounding gets even more effective, and we get the tighter bounds. All this wasn't too quick. How this wasn't too slow. I will now switch to what I already foreshadowed, is the bounding of the parametric differential equations, where yeah, I promised in the title that we are dealing also with the dynamic global optimization, where we don't have a factorable function if we don't know the exact solution of a differential equation, which might be involved. And of course, the idea is, how can I find out the not necessarily at the first point, not necessarily convex and concave envelope. For example, if we are in a time domain, if that would be interesting for some reason. But at least upper and lower bounding solution. And in this simple example, where I have just one parametric uncertainty, you might say, which takes an interval value, even the picture tells us that I can construct the basically using the interval methods, I can construct the auxiliary differential equation systems, which then give us upper and lower bound, and catch all the values that the x that the state can take, no matter what the value of the parameter from this interval is. Yeah, that's the basic simple idea, which looks very nice in 1D, but let's switch to my one of the favorite examples. Some of these examples are getting very aesthetic if you use the right colors. Just the 2D case, and well, this is now x1 and x2 is our state space. So basically, our dynamics is propagated. Our uncertainty here lies in the initial conditions. They are lying in some ellipsoid. And basically how this nonlinearity in the dynamics propagates, we are getting these nice shapes. And the question is where I can see here my previous upper and lower bounding problem, how to go about it. Well, the first idea is to basically try to box the solution in a state space in each time interval. And this is the method which is known for years. It's based on interval arithmetics, and it basically says that our upper and lower bounds are found as a supremum infimum. Basically, we are at each point in time trying to find what is the largest slope among the values that the right hand side of the differential equation can take, and what is the lowest of the slopes. And this is basically how in 1D this would be constructed, and of course in 2D we have the upper and lower bound for each of the states, so effectively boxing the solution. What then happens if we try this in this nice toy example in this nice example is great example of the deterministic chaos. So there is just a little bit of the, you might be tempted to say, noise in every revolution of the dynamic system, which then can cause these interval bounds to actually explode pretty quickly. And why is this? I just show you another example, and this part of the bounding of the parametric differential equations, it's called the wrapping effect. So even if we have this nonlinear dynamics, our initial point lies in this box. If we just simulate by one time step, and then we are boxing. So we want to find we want to have upper and lower bound with respect to x1 and upper and lower bound with respect to x2. Well, basically in the next time step, this really is wrapping. We are including some parts of the solution which are not really a solution, but we are doing it because we want to be guaranteed. So how to fight this? One of the possibilities that we worked on was using again Taylor models, where the idea is basically very same as if we have any form of algebraic function. Well, we can construct a polynomial which would be basically approximation. If this was a first order polynomial, that is basically some linearization of the dynamics. If it's second order, third order, it's a polynomial which might be then constructed the same way as a Taylor expansion says. So these derivatives here are nothing than just parametric sensitivities. Many ODE solvers supply this information for free, so that's fine. How to deal with the remainder? So basically the remainders should then, if I show it in this format, just in the state space in one trice of time, so should then basically make our solution valid, and our bounds valid. So, well, these are already suggesting some kind of interval boxes, and yes, that's the point. We already caught a lot of these non-convexities, this non-standardness of the shapes. So it's by the polynomial part, and then we are fixing the rest basically with the remainder part. And yeah, basically I will skip this. This is just a formulation of how we can find and relatively easily construct these remainder bounds. And then, since well, our Taylor model can have different order, that depends on the polynomial. So how much wrapping effect, how much dependencies we expect in our solution, that's the tuning factor. Then basically what is shown here, how the Taylor model of the second order, how the Taylor model of the fourth order is fighting with this nice little problem. What can be also shown is the convergence, and now this is form of Hauser convergence. So if my uncertainty would shrink a little, how much would my overbounding would my error of the overbounding basically shrink? And this is linear for the interval methods, but we can really say this Q is a order of the Taylor model, so this can be tuned. Of course, it comes comes with the price of the computational complexity. Let me maybe just briefly show you, as I don't think I have time, and I would rather be discussing with you what were the applications. So we basically said, okay, the global and dynamic optimization is interesting. I will show you even some tools that are available from that and for that, and that implement these methods. But we looked at the problem of the guaranteed estimation, and basically this problem is just trying to find, if we are given a set of measurements which have the minimum and minimum and maximum bound on the measurement error, and no information about the statistical distribution of the error. So this problem is just trying to find all the parameters that would if plugged into the model, would give these trajectories that would basically fit those measurements. So it's standard set membership or guaranteed parameter estimation. And yeah, this can be posed let's not go into detail. Maybe just look at this simple form. This can be posed as the set computing problem, because we are basically trying to find all the parameters that fulfill some bunch of nonlinear, non-convex inequalities. And well, why did I mention the global optimization and the spatial branch and bound in the beginning? Well, this is again applying some branching, finding the boxes which do not represent the property that we want, finding the boxes that represent it, and finding the boxes which are undecided, and then combining them together. I will just switch to show you that this. So what is in the solution procedure? Well, we are branching the parameter space because we are looking for a set in the parameter domain. We are taking a parameter box, constructing a Taylor model in order to bound the nonlinear, potentially nonlinear dynamics, and then we are deciding whether the picked box really is part of solution or not. And this is implemented in the libraries MC++. That's for the static and for the factorable functions, and Chronos, that's for dynamic problems. Those are the libraries which are primarily maintained by Benoit Chachuat at Imperial College London. The QR code here points you to the web page of Benoit, where he lists where you can find these softwares if you wanna try. They are in C++, but there is already MC++ is available as a third-party library through Pyomo if you like using Python. What these convexification and bounding tools can do for us, and I'm just not expecting that in this one minute I'm going to talk about this. You will completely understand if you haven't seen this before. Well, we can do some nice. We can exploit the properties of the convex relaxation, how I showed in the beginning, and we can start tightening the domain of our parameters, of our decision variables in the global optimization. And in several applications, this really proves to be really nice and fast way of approaching to the solution. So this is basically just the comparison. The dashed lines are the CPU time with no domain reduction. So if we are not really exploiting the convex relaxation, the CPU times are dropping really nicely. Yeah, that would be it. I don't wanna run too much over the time. I think Andreas told me something like 40 minutes, so I just show you again the QR codes for the slides for our European projects, where you are all very welcome to talk with us, to exchange with us at some events or wherever. And also there is a QR code for the software if you want to try. Thank you very much for your attention.
Okay, then many thanks, Rado, for your very interesting presentation. And yes, let's start with our question and answer session. Who wants to start? Okay, then let me start. I've written down, I think, at least 4 questions. The very first question that I have is, because you just mentioned, yes, the reduction by means of optimization techniques at the end. Maybe you could talk a little bit further of how you see interfaces of this with some kind of predictor corrector state estimation that you have, for example, continuous time dynamics with discrete time measurements, where you would use the measurements as some kind of optimization. And yes, the reason why this comes up to me is just because our next speaker on Friday in 2 weeks will be Nassim Ramdani, and he'll also use such predictor corrector approaches for the construction of impulses observers. Maybe you could explain a little bit more how you see the interfaces of your techniques with this.
Very good question. I'm happy that you are mentioning it. My PhD student Carlos just spent some time in the Nassim's group, and he was working on a similar problem. So this is very early question to the point. And yes, there are tons of possibilities of the opportunities there. Basically, wherever you can formulate your set-based, your search problem in a form of inequalities, well, basically you can do also sorts of tricks, the convex relaxation, and then you are basically getting into much nicer optimization problems. What I didn't mention, okay, you don't have to really rely on general purpose general purpose convex solvers. You can even do some nicer stuff with these. You can basically try to even linearize the convex function, and then you are basically in the realm of linear programming methods, where the solvers are really fast, accurate, robust, and they can deal with tons of variables. Do you also mean some specific nuances of Nassim's estimation that you see a potential?
No, I think why I was asking this is because what Nassim is doing is he's typically using the dynamic system formulation. He has discrete time measurements. The assumption of his continuous time system model was in the background. And then he's more or less doing some kind of interesting way how to reduce uncertainty by taking into account the measurement information. And those are physical measurements that he's using. For example, position measurements of a robot, velocity measurement. The direction into which I was thinking is if you're trying to find bounding solutions for an ODE, the assumption to find those bounding solutions is more or less, if you have guaranteed boundaries or non-conservative boundaries, you need monotonicity properties of your system. Quite often they are not maybe directly visible, but our system may have them because, for example, if you're coming from the field of chemical engineering, you know there would be some compartment models, for example, conservation of mass, conservation of energy in the background. And when you think about thermophyletic systems, what you could do is, for example, you could sum up some of the state equations, and a weighted sum of the state equations would be something like the balance of internal energy. And did you try to include such a strategy? Because this would be a side constraint on the maximum variation rates of a quantity that is deduced from the state variables. Did you try to include something like this also in the solver that you have for solving by using Taylor model techniques, the ODEs?
Yeah, that's a good point. We actually haven't tried this. I know of some approaches in this direction. Well, basically, in the standard global optimization, people are doing redundant constraints approaches. So basically, those are only the algebra. Even at the algebraic domain, you can reformulate your standard pooling problem in several ways. So basically, if I am okay, I have a different PDF viewer, and I wanted to jump right forward. basically, if I'm just in this problem, right? I tried. I don't know what is the right factorization to get rid of the dependency problem. I can try several factorizations and combine them together to improve the quality, because different factorization would in the multivariable domain result in different cuts of the subdomains, and yeah, this can be exploited. Of course, this would then come for the cost of the computational time, but yes, if you find the right balance, and yeah, there are people who try to exploit something like this in the chemical engineering domain, then yes, you are on the right track. We yeah, we weren't dealing with that, but yeah, that's possible.
It's because I think it would be really is, let's say, a nice case when also Taylor models could be used for this efficiently, because I think now, maybe Katja can help me. I think we did it around 10 or 12 years ago, that we just used very simple interval calculus for predicting the states of, this was a high temperature fuel cell, where you have such kind of balances. And yes, there the thing was, or what we at least figured out, is using extremely simple shapes was more efficient at the end to predict the dynamics, and to add at the end such conservation properties was more efficient than using more complex shapes and try to propagate, for example, the set of solutions by Taylor models or higher order temporal series expansions.
Yeah, that might be the case. There are tons of very nice tweaks, very nice combinations of the methods, which if you are trying to, for example, let's say you are trying to build a commercial solver for this, or some solver that is not a research solver, let's say, but that people around the world should use, then you would love to have all these methods around. What I was showing here, for example, so basically this axis here shows the quality of the solution. If you will, it is similar to the epsilon in the global optimization. So if we are we found out, okay, the Taylor models of the several orders do much greater bounding than the interval arithmetics, and even if we use these nice little tricks like domain reductions, if we want a coarse solution, then we are saving a lot of time, a lot of computing burden and stuff like that, because we are excluding the non-progressive boxes very early in the calculation. But if basically our calculation proceeds, this is getting too much. This is exactly where we should have switched maybe to interval arithmetics. Yeah. Mm-hmm. So I mean, great point that you are mentioning. It's exactly that. We did that. We did in what we did in the follow-up work. We tried to reuse part of the solutions of the Taylor models. Like, we do not need to simulate again and again all the parametric sensitivities and stuff like that. We can from some point in time work with lower order Taylor models, because we are saving computational time, and then it doesn't benefit because we already have smaller boxes where we are searching for. Yeah, there are tons and thousands of the methods and the combinations. Yeah, that's, I don't know whether it's an open problem or it's but it's definitely an interesting question to ask. Why not combine all these methods? Why not searching what works where? Maybe finding some nice tips and heuristics.
Yes, I think it's even, or let's say, an extremely application-specific question at the end.
Exactly. Yeah, for sure.
Yeah, and the last question that I have on my list of notes is this system where you showed yes, this deterministic chaos behavior, you lot call the Terra model. That's one of the models when you have point valued parameters where you have yes, exact limit cycles.
Yeah.
Did you include some strategies, for example, for proving stability of limit cycles by using, for example, some Poincare maps?
I don't think it's exploited here. Yeah, well, that's another interesting point. Yeah.
The thing is, because here in our series of seminars, it was Daniel Wilczak who gave a talk on this, and I think in his CAPD solver, he has the option to compute Poincare sections. And this, for such kind of specific problem, this could easily be exploited. And yes, someone who also used this recently is Luc Jolin, who used either ellipsoidal enclosures or interval enclosures to prove also yes, the stability of navigation cycles of an autonomous sailboat robot. Yes, and therefore this could be also a nice extension, maybe to just look into the capabilities there of CAPD.
Yeah. Wrote it down. Thank you very much for the tip. Yeah. Perfect.
Okay, do we have any other questions? I see that Marek is thanking you for your excellent presentation.
Thank you very much for coming.
Okay, now let's see. Further questions? If yes, please unmute yourself and ask the question. If not, again, many thanks, Rado, for your excellent talk. And yes, as usual, we'll put them on the webpage, the slides, and also the link to the YouTube recording. And from that point of view, to all of you, have a nice Friday afternoon, evening, weekend. And we'll meet each other on Friday in 2 weeks for the last presentation before Christmas. And the last speaker before Christmas will be Nasim Ramdani, who'll talk about, yes, slightly related work, in fact, where he'll use also, yes, predictor corrector state estimators or also impulsive estimating schemes for continuous time dynamic systems. And have a nice weekend.
Thank you very much. Have a nice weekend too.